Imagine this. You have spent weeks calibrating your rainfall runoff model. You achieved a great fit between simulated and observed hydrographs. But here's the problem. What if your rainfall input, the very thing driving your model, is wrong by plus minus 20%? Suddenly, all that careful calibration doesn't matter anymore. This is the classic garbage in, garbage out problem. And in hydrology, rainfall uncertainty is often the largest source of error. In this video, we will break down where rainfall uncertainty comes from, how it impacts our model, and what we can actually do about it. Let's get started. Let's start with where rainfall data comes from and why none of it is perfect. Rain gauges look simple, but they come with major issues. Wind-induced undercatch can reduce measurements by 5 to 50%. Wetting and evaporation losses bias light rainfall events, and daily data loses critical sub-daily rainfall information. Weather radars give us great spatial and temporal resolution but introduce new errors. The ZR relationship uncertainty can cause rainfall errors up to plus minus 50%. Beam geometry issues lead to overshooting, vertical gradient errors, or range degradation. Attenuation, on the other hand, underestimates heavy rainfall, and calibration drift introduces systematic bias. So, while radar provides invaluable spatial and temporal resolution data, it's not perfect. Satellites, on the other hand, are essential in data-sparse regions, but infrared estimates can have 50 to 100% uncertainty for individual events. While passive microwave improves this, they still have 30 to 50% uncertainty. Merged multi-satellite products reduce errors but still have 20 to 60% uncertainties depending on region and rainfall regimes. Although merging gauge, radar, and satellite data makes the data better than individual sources, it still has 15 to 35% uncertainty. Even if measurements were perfect, we still introduce uncertainty when preparing inputs. This is related to the spatial and temporal uncertainties. First, spatial uncertainty. Converting point data to catchment rainfall introduces errors. For example, simple approaches like TSN method have 20 to 50% error. Advanced geostatistical methods like cryoging have typical 10 to 30% error. Convective storms and complex terrains make this even worse. Second, temporal uncertainty. Many models need high-resolution rainfall, but data is often coarse. Disaggregation methods like daily to hourly introduce 15 to 40% uncertainty. Storm duration and timing errors, on the other hand, can shift the flood peak and affect the runoff volume. Rainfall errors don't propagate through models linearly. A 10% rainfall error can produce 15 to 30% runoff error, and a 20% rainfall error can produce 30 to 60% runoff error. In fact, error propagation is complex, nonlinear, and model dependent. So, what's the reason for this nonlinearity? Let's explore it. First is threshold processes effects. Small rainfall errors near thresholds, such as infiltration capacity, soil saturation, or channel bankful conditions, can cause large runoff errors. Second is catchment state dependency. A wet catchment can amplify errors, while a dry catchment can dampen them. Third is spatial rainfall effects. Rainfall concentrated on certain land use, for example, urban areas or forests, can amplify or dampen runoff errors. Then come the model structure effects. Different model types propagate rainfall errors differently. Lumped models have a simple error propagation. Catchment average rainfall error could produce predictable runoff errors. However, spatial patterns error remain invisible to the model. Semi-distributed models, on the other hand, can partially capture spatial pattern errors, but sub-catchment rainfall errors propagate independently. Fully distributed models are the most sensitive ones to spatial rainfall errors. Pixel scale rainfall errors aggregate nonlinearly and can amplify or dampen errors depending on catchment organization. It is worth noting that calibration can hide rainfall errors. For example, if rainfall is underestimated, calibration increases the runoff parameters. The model appears accurate, but only for that dataset. Finally, note that some catchments are more sensitive to rainfall errors than others. Examples are urban catchments, small basins, steep terrains, and shallow soil catchments. So what should we do? First, understand your project needs, for example, the required spatial and temporal resolution. Second, use multiple rainfall sources. Always cross-validate your data and identify systematic biases and inconsistencies. Third, apply quality control. remove unrealistic values, check spatial and temporal consistencies, and ensure physical plausibility. Fourth, quantify rainfall uncertainty. Use approaches such as ensemble modeling, sensitivity analysis, and multi-product comparison for this. Fifth, calibrate more carefully. Use multiple rainfall products. Treat rainfall as an uncertain input to be estimated alongside parameters, and always aim for robust parameters, not perfect ones. Finally, communicate rainfall uncertainty. Avoid false precision and report the sensitivity. Uncertainty isn't weakness, it's realism. Rainfall uncertainty is unavoidable, but we can understand it, quantify it, and account for it in our models. Because in the end, a model is only as good as its inputs. If you found this video helpful, stay tuned, because in our next videos, we will go deeper into hydrological modeling and how to deal with it in practice. Thank you for watching. See you in the next one.